In this video, I will discuss manifold learning. I will also implement manifold learning techniques such as multidimensional scaling in Python. Although principal component analysis is a simple and easy method for dimensionality reduction tasks, it does not perform well for maintaining nonlinear relationships within the data. To address this deficiency, we use another type of methods known as manifold learning. These are a class of unsupervised estimators that seeks to describe datasets as low-dimensional manifolds embedded in high-dimensional spaces. For example, we can fold a two-dimensional piece of paper to create a three-dimensional object. We can think of this piece of two-dimensional manifold embedded in three-dimensional space. Folding a paper to create three-dimensional object doesn't change the flat geometry of the paper. This is called linear embeddings. Manifold learning algorithms will try to learn about the fundamental two-dimensional nature of the object even as it is embedded in three-dimensional space. We will now illustrate this concept in Python. Let's generate two-dimensional text data that will be used to understand manifold learning. We start with the importing standard libraries and writing a function to visualize the result. Let's call the function and visualize the resulting data. This two-dimensional shape of word will help us to see visually what these algorithms are doing. If we try to understand the data from this image representing a name, we can observe that the particular values of x and y coordinates are not the most fundamental explanation of the data. We can rotate, scale, or shrink the data and the word will still be evident. For example, we are going to rotate the data using a rotation matrix that will change the x and y values, but the data representing the word would fundamentally be the same. This tells us that the x and y coordinate values here are not certainly a fundamental representation of the data, but what is fundamental here is distance between each point. Programmatically, it can be represented by a two-dimensional array or matrix. We can calculate this pairwise distance between points in Python using scikit-learn package. If we similarly can construct a distance matrix for our rotated and translated data, we see that even if we have rotated the data, distance between points is the same. Computing distance matrix from the coordinates is straightforward, but transforming the distances back to coordinates is not that straightforward. This is what is done by the multidimensional scaling algorithm. It recovers a d-dimensional coordinate representation of the data. Let's see how it works for our distance matrix using the pre-computed dissimilarity to indicate that we are passing a distance matrix. The MDS algorithm recovers two-dimensional coordinate representations of our data using only the distance matrix, defining the relationship between the data points. This is very useful in manifold learning since distance matrices can be computed for data in any dimension. So, for example, instead of simply rotating the data in the two-dimensional plane, let us illustrate this with our example. We can project our word image into three dimensions as shown in the Python code. Let us visualize this three-dimensional data. We can now use the MDS estimator to compute the distance matrix from three-dimensional data, and then we will determine the optimal two-dimensional embedding for this distance matrix. This should recover the original data representation. This was basically we were expecting from manifold learning estimator to convert a high-dimensional data into low-dimensional representation. This brings us to the end of the discussion. See you in the next video. Thanks for watching.